odd and even mode. Since in this course we will require to know about simple microwave circuits, there are two types of circuits, active circuits and passive circuits. Active circuit we have started already, discussions about amplifiers. Now we will switch to passive circuits, simple passive circuits. We will discuss some simple passive circuits. This simple passive circuit analysis will require sometimes the concept of even mode and odd mode. Therefore, today we will discuss the concept of even mode and odd mode. And try to give you some concept so that you understand what is even mode and odd mode. And when we use it, you will see how they are useful, how they are applied in practical circuit designs or analysis. Remember that this part, even mode and odd mode, as such are not part of your course, but their applications are a part of your course. So we'll develop the concept of even mode and odd mode. We'll start with circuits, simple circuits, electrical circuits or electronic circuits. Then we'll see about microstrip lines or transmission lines, the concept of even mode and odd mode in electrical circuit, resistor circuits. First I'll start, then we'll go to microstrip line and see the concept there. So, when you look at electronic circuits, at high speed we call it these microwave circuits because the frequency is in the microwave range. Those circuits are mostly symmetric in nature. Most of the circuits that you will design, they will be symmetric in nature. Since they are symmetric in nature, it becomes easier to analyze those circuits. So analysis becomes easier with symmetry. Always, whether it is circuit, whether it is a device, anything that you take, any physical entity, if it has symmetry, the analysis becomes easier because half of that or 1/4 of that you can analyze, then you can extend it to the whole circuit. So analysis becomes easier, it is less cumbersome, less computing time, less effort is required in the analysis. Microwave circuits are mostly symmetric, but with that comes a caveat. The caveat is, although they are symmetric, the circuit looks symmetric, it is unlikely that they will be having symmetric sources. So if there is one source, then it is asymmetric. If there are more than one source, then both the source may not be symmetric. So although the circuit will be symmetric, it is unlikely that sources will be symmetric. If the sources are not symmetric, then overall circuit is losing its symmetry. So then the analysis becomes difficult. So in such case, where without the source the circuit is symmetric, with the source the circuit loses its symmetry, how to use the available symmetry in the circuit for its analysis and make the analysis easier is the topic of our discussion today. Suppose we have asymmetric sources. We have a symmetric source, but we have asymmetric sources. In the asymmetric sources, if we have asymmetric sources, then what we can do is we can assume that in the circuit there are virtual short circuits or virtual open circuits. They are useful. Conditionally, under certain conditions, virtual short circuits will be useful, virtual open circuits will be useful. For example, what is a virtual short circuit? You know, a short circuit means there will be infinity current and zero voltage. So forget the current, but voltage is zero. So in this circuit, wherever you find that voltage is zero, we can assume that that point is virtually shorted. So voltage Because that. Similarly, if at any point we find that current is 0, then we can say that that point is virtually open point. So those are virtual short circuits and virtual open circuits. They can be conditional under certain conditions. They will be useful in analyzing the circuit. What are the conditions under which this will be useful? Condition is the circuit elements that we are using, except the sources, the circuit elements are linear and independent upon each other. The sources have to be independent upon each other. Then if they are linear and independent, that leads to a very good condition, that is the superposition condition or principle of superposition. Linear sources, independent sources, linear and independent sources, linear and independent components, they always obey the superposition principle. If the superposition principle is obeyed, then it is possible to analyze the symmetric circuit with non-symmetric sources. So what we will do is use one non-symmetric source, find out the response of the circuit, use the other source, find out the response of the circuit, then add these responses. That is the combined response of when both the sources are present. So that is why it is important. So let us consider a simple circuit. Example, we will consider a simple circuit. The left hand side, look at the left hand side. The left hand side is the circuit. It is a two-port circuit. We can see the two ports. In this circuit we have 200 ohm resistors are in series, but in between them there is a shunted 50 ohm resistor, and across these 200 ohm resistors there is a 200 ohm resistor. And if you look at this from the center, it looks symmetric, but at the top there is a 200 ohm resistor that is causing some asymmetry. So what we can do is, a 200 ohm resistor is same as series connection of 200 ohm resistors. So the top 200 ohm resistor is equivalent to 200 ohm resistors. So look at the right hand side. In the top line there are 200 ohm resistors. So 200 ohm resistors are in series, which means that is giving to 200 ohm resistor, 200 ohm resistor. So that part is taken care of for the first part. Then the 50 ohm, that should be divided equally between the two parts of the circuits. So 50 ohm, you know, is equivalent to parallel connection of 200 ohm resistors. So for 50 ohm we can replace that with 200 ohm resistors. So the right hand circuit is same as the left hand circuit. It will behave exactly in the same manner as the left hand circuit. So if we are to analyze the left hand circuit, we can decompose it into the right hand circuit, and we can then analyze the right hand circuit. Now if you look at the right hand circuit, draw a line exactly at the center of the right hand circuit, then on both the sides of the circuit line the circuit elements are same. On left hand side the circuit elements will be 100 ohm, then there will be L 100 ohm, and with the L there will be parallel 100 ohm. On the right hand side equally same. So both this is the along that vertical line, this circuit is symmetric. Now let us say that we want to find out the admittance matrix of this circuit. It is a two-port network. Since it is a two-port network, its admittance matrix will be Y. Y will be Y11, Y12, Y21, Y22. These are the elements of the admittance matrix. Y11, Y12 are the elements in the first row. Y21, Y22 are the elements in the second row. Our job is to find out what will be Y11, what is Y12, what is Y21, what is Y22. Now just look at the symmetry of the circuit. Because of the symmetry of the circuit, you can say if I find out Y11, I can easily find out Y22 because Y11 will be equal to Y22. If you look from the port 1, the resistances that is seen will be exactly same as the resistance that I will see if I look from port 2. Therefore, Y11 will be equal to Y22. Similarly, Y12 will be equal to Y21 because of symmetry. Now you can know the advantage of symmetry. Now the advantage is, instead of calculating the 4 elements, it is now reduced to calculating in only 2 elements. Y11, Y12 if I calculate, then I can find out what is Y21, what is Y22, because they will be same using this. Now let us start with the analysis for finding the Y parameters or the admittance parameters. What we will do is, we will sort one of the ports. The port 2, let us short circuit the port 2. If we short circuit the port 2 and look at this circuit now, look at the circuit, short circuited the port 2. In port 1 we are giving the source Vs. If we give Vs, the source is connected to port 1. At the port 1, let us say the voltage is V1, and at port 2, let us say the voltage is V2, and port 2 is short circuited. Now this is a classic case of asymmetric sources. On one side we have V1, other side we have V2. V1 is not equal to V2, V1 is equal to Vs, whereas V2 is equal to 0, short circuited. So this is the sources are asymmetric. So because of the asymmetric circuit due to sources, the sources have made this circuit asymmetric. You can see that there is no virtual ground, there is no virtual short circuit in this circuit. So in this form there is no virtual ground, there is no virtual circuit short. How to analyze that? Now to analyze that, let us remember simple things that we studied when you are in the plus 2 science. First, let us model the source at port 1. At port 1 we have Vg. Suppose we have the Vg. Okay, Vg is the source at port 1. Vg, Vg is a voltage source which is connected to port 1. That is equivalent to 2 voltage sources, each of Vg by 2 and connected in series, which means the negative end of the source Vg by 2, source 2, will be connected to positive end of Vg by 2. That way, if you connect, it is a series connection. So if they are connected in series, then Vg is equal to Vg by 2 plus Vg by 2, which is 2 equal sources, 2 equal voltage sources are in series. So for port 1, we can replace the voltage source by this Vg, that we can replace as Vg by 2, 2 sources by 1 source we can replace as equivalent to 2 sources in series, Vg by 2 and Vg by 2. Now what about source 2 at port 2? Now at port 2 the source is 0. So what we will do is, for the short circuit at port 2, we will take 2 equal voltage sources, but they are opposite in sign. So 2 equal but opposite voltage sources are in series. So plus of one is connected to minus of the other. So if we consider one source to be minus Vg by 2, other source to be Vg by 2, and add them together, then Vg by 2 plus minus Vg by 2, that is equal to 0. So that is short circuit. So net voltage will be 0. So 0 voltage or short circuit is equivalent to connection of 2 equal but opposite voltage sources. That is what is the short circuit. Now use this concept in the circuit. So we have unequal sources at two ports. That has given us asymmetric circuit. Now what we are doing is we are turning up the bottom. So we take now these two unequal sources to be on the left hand side. We take, or at the port 1 we take two equal sources in series of half the amount. So Vg by 2 are in series on left side, or on the port 1. On port 2, two equal but opposite sources. So Vg by 2 minus Vg by 2. What we will do is, first we will turn off the bottom sources. If we turn off the bottom sources are Vg by 2 and minus Vg by 2. They are turned off means they are made 0. If they are made 0, then we are restoring symmetry, because at port 1 the source is Vg by 2, at port 2 also the source is Vg by 2. So Vg by 2, Vg by 2, so that is restoring the symmetry around the dashed line. If you look at the dashed line at the center, vertical dashed line at the center, around that vertical dashed line the circuit is symmetric including the sources, because the bottom sources are 0. So including these sources, this is symmetric. Okay, next. Now with that comes the concept of even mode. So we will discuss the even mode now. Now what we have done is we have restored symmetry. How we have restored symmetry? We have switched off the bottom sources. By switching off the bottom sources, we have restored symmetry. Now when we restored symmetry, then along the center line, along the dashed line, we have an virtual open symmetric plane. Why we call this to be a virtual open symmetric plane? Now look at this line, and where this line cuts the circuit, any point on the circuit, you look at that point. At that point the current will be 0. Why? And now from the left hand side we have, from the port 1 we have Vg by 2. So current I1 is going. Current I1 sees echo at the first junction. It sees two impedances. One is towards the upward, one is towards the downward. And so some current will go upward, some current will go downward. When the part, how it is divided? Upward it goes for 100 ohm, downward it goes for 100 ohm plus 100 ohm. Okay, so that is how it will be divided. From the port 2, it is equally divided. Since in the same manner it is divided in the port 2. Now at the top line, if you consider the current coming from port 1, which is passing through the 100 ohm resistor, will be exactly same as the current coming from port 2 and passing through the right hand side 100 ohm resistor. So since both the currents will be same, but they will be in opposite direction, at the center point or the dash point where it meets, at that point it will be 0. The net current will be 0 because it is equal and opposite. Similarly, at the other points where it is intersecting, there it will be 0. Since current is 0, it is virtually an open circuit. You know, in the open circuit the current is 0. So virtually this is a plane which is representing an open circuit. This dashed line gives a plane which is representing an open circuit. When the circuit operates in this mode, the mode of the circuit is called even circuit. So this is an even circuit mode. The mode is even circuit. The analysis that is done for this circuit is called even mode analysis, because the circuit is operating in even mode. Its analysis is called even mode analysis. Then the solutions, once you do the analysis, we will get the solutions. The solutions, in the solutions what we get? We get the current, we get the voltage. So the current that we get by analyzing the even mode circuit using the even mode analysis, that current is called the even mode current. Similarly, that voltage is called the even mode voltage. So the solutions of in the even mode, the solutions give us even mode current and even mode voltage. Now let us do the even mode analysis. One half we will take, because of the symmetry, so we will take the port 1. So port 1 side, let us take the port 1 side. If we consider the port 1 side, along the symmetry line, the current is 0. So that is the open circuit. Along the symmetry line, the current is 0, that is open circuit. So now we have to find out what will be current entering the circuit at the port 1. So that is I1. I1, 1 stands for port 1. I1, then E, the superscript E stands for even mode. We are doing even mode analysis, that is why it stands for even mode. So I1E is equal to how much? I1E is equal to Vg by 2, that is the voltage, into the voltage into the admittance. Now what is the admittance, total admittance? You can see the upper 100 ohm is connected to open circuit, so that is not giving any contribution. The contribution is because of the lower 100 ohms, 200 ohms. They are connected in series, 100 ohm plus 100 ohm, that is 200 ohm. So I1E is equal to Vg by 2 into 1 by 100 plus 100. 100 plus 100 comes because of the series connection of the 200 ohms below, lower 200 ohms. So 100 plus 100 is 200. So it is Vg by 2 into 1 by 200. 1 by 200 into 1 by 2 is 400. 1 by 400. So I1E is equal to Vg by 400. Now if I look from the port 2, I will see exactly same circuit, similar circuit from the port 2. Therefore the current that is coming from port 2 in the even mode will be I2E, that will be same as Vg by 400. So we have got I1E is equal to I2E is equal to Vg by 400. So now what we have got is the currents, even mode currents at the two ports. We have got I1E and I2E, the even mode currents at the two ports. Similarly, we have also got the even mode voltage at the two ports, Vg by 2, Vg by 2 for this analysis. Now let us come to what is called an odd mode analysis, or what is an odd mode. Let us try to understand that. Now for odd mode, what we will do is, now we will switch off the top two sources, which is Vg by 2, Vg by 2 at both the ports. So the top two sources are switched off. Now what are the bottom two sources? At port 1 it is Vg by 2, at port 2 it is minus Vg by 2. So port 2 is exactly same as port 1 voltage, except it is opposite in sign. Port 1 and port 2 sources are same, except they are opposite in sign. So we have switched on the bottom sources, switched off the two top sources. Now the symmetry of the circuit is odd, because on the left hand side we have a positive source, on the right hand side or port 2 side we have a negative source. So symmetry of the circuit is odd. This odd symmetry gives us an odd mode circuit. So circuit mode is odd. This effectively leads to a virtual short symmetric plane. In the even mode, we had got a virtual open symmetric plane. Here we will get a virtual short symmetric plane, because the voltage along the line of symmetry will be 0. Now that you can, as we have seen in the previous case, here also you can see, in the previous case we saw that the current is 0. In this case you will see that voltage is 0, that you can easily calculate, find out mental math. Using mental math you can find out that the voltage is 0 along the line of symmetry. Since it is along the line of symmetry, it is 0. The plane passing through the line of symmetry is called virtual short symmetric plane. The circuit on its odd mode is called the odd mode circuit. The analysis is called odd mode analysis. The solutions will give odd mode current and odd mode voltage. Solution of the circuit. Solutions means when we solve for the circuit, we will get odd mode current and we will get odd mode voltage at port 1 and port 2. So let us evaluate, do the analysis and evaluate the odd mode half circuit. This is evaluating odd mode half circuit, not even mode. Even is a mistake, typographical mistake, make it odd mode. So evaluating odd mode half circuit. I1 I1 is at port 1, O is odd mode, that will be equal to Vg by 2 into 1 by 100 parallel 100. Why 100 parallel 100? Now there are three resistors, 100 ohm, 100 ohm and 100 ohm. The bottom two resistors are in series, but we are saying that it is 100 ohm parallel 100 ohm. Why it is so? Because if you look at the bottom part, it is open circuit. It is short circuited. Since it is short circuited, at the bottom part, the voltage across the 100 ohm resistor, the lowest resistor, voltage across that will be 0, because that those ports, that plane is short circuit, virtual short circuit plane. So across that plane, voltage is everywhere 0. So along that plane, voltage is everywhere 0. So across 100 ohm, the lower bottom 100 ohm, the voltage is 0. Voltage is 0 means as if that 100 ohm is not there. So that is the option. Above, if you look at the top 100 ohm and the middle 100 ohm, so the voltage between these two is 0. That is not a point, which means if the voltage is 0, those two are connected in parallel. Therefore, those two, the top and the middle, are connected in parallel. Lower 100 ohm is absent. Effectively the lower 100 ohm is absent because the voltage across the lower 100 ohm is 0, considering the short circuit. Therefore, I10 is equal to Vg by 2 into 1 by 100 ohm in parallel with 100 ohm. 100 ohm in parallel with 100 ohm gives us 50 ohm. So it is Vg by 2 into 1 by 50, that is equal to Vg by 100. Now, since the sources are equal but opposite in nature, so the currents will also be equal but opposite in nature. So I10 will be equal to minus I20. So I10 equal to minus I20 equal to Vg by 100. So we have done the odd mode analysis, and in the odd mode we have found out the currents at the two ports, port 1 and port 2. The odd mode currents are I10 is equal to Vg by 100 and minus I20 is equal to Vg by 100. Then our job is to find out the total current and total voltage. So total current, total voltage, how we will find out? Using the superposition principle. So use the superposition due to even mode and odd mode, that will give us the total voltage and total current. First find the total voltage at port 1. So V1 is the total voltage at port 1, that is equal to Vg by 2 plus Vg by 2, which is equal to Vc. Voltage at port 2 is Vg by 2 minus Vg by 2. At port 1 it is Vg by 2, at port 2 it is minus Vg by 2. So Vg by 2 minus Vg by 2, that is equal to 0. So V1 and V2, that we have found out. V1 is equal to Vg, V2 is equal to 0. Then we will find out the odd mode current, even mode plus odd mode current. So devices of the circuit are linear. Here we have seen we are using only resistors. There is no non-linear component, which means no transistor is there. No diode is there. So there is these circuit elements are linear. Since circuit elements are linear, superposition principle is applicable. If superposition principle is applicable, total current is equal to current due to even mode plus current due to odd mode. So find out the current at port 1. Current at port 1 will be I1, that is equal to I1E plus I1O. Similarly, current at port 2 will be I2, that is I2E plus I2O. And you know I2E is equal to I1E. So that will keep as it is. But I2O is equal to minus I1O because of the negative voltage. So I2 will be I1E minus I1O. We have found out expressions for I1E and I1O. Those we will use now. Using that, I1 is equal to I1E plus I1O. That will be I1E is Vg by 400 plus I1 odd is equal to Vg by 100. That gives us Vg by 80. I2 is equal to I2E plus I2O, which is equal to I1E minus I1O. So that is equal to Vg by 400 minus Vg by 100. That will give us 3 Vg by 400. So this will be minus 3 Vg by 400, not 3 Vg. This will be minus 3 Vg by 400. So I2 is equal to minus 3 Vg by 400. So now we have found out what is V1, what is V2, what is I1, and what is I2. Since that we have found out, we can find out what is Y11. Y11 will be equal to, by definition, admittance parameter. Y11 is equal to I1 by Vg1 when Vg2 is equal to 0. Now put the value of I1, which is Vg by 80 divided by Vg1 is Vg. So Vg by 80 into 1 by Vg, that is equal to 1 by 80. Similarly, Y21 will be equal to minus 3 Vg by 400 into 1 by Vg, that is minus 3 by 400. Similarly, using symmetry of the circuit, we can say Y22 is equal to Y11 is equal to 1 by 80. Y12 is equal to Y21 is equal to minus 3 by 400. So the 4 elements we have found out. So the calculated admittance matrix of the circuit now becomes Y is equal to 1 by 80 minus 3 by 400 minus 3 by 400 and 1 by 80. These are the matrix elements of the admittance matrix. So the advantage of even mode odd mode analysis you can see from this. It became very simple to analyze the circuit using even and odd mode concept even when the asymmetry crept in. So circuit analysis we have seen about even mode and odd mode, and I hope you have understood the advantage of even mode and odd mode, what is even mode and what is odd mode, and how to do the analysis. That you have understood. Let us extend that concept from the discrete circuits to distributed circuits or microwave circuits. For that, I will take an example of coupled lines. Let us consider two traces on a PCB. Let us consider two traces or two microstrip lines. So line 1 and line 2. Consider a digital circuit. In the digital circuit, we are going to use two lines to transmit one logic level 1 or logic level 2 and logic level 0, that will transmit using the two lines. So comparing the logic level, comparing the voltage at one line with respect to the other line, we will get the logic. So what we will do is we will find the impact on the impedance of the main line. Suppose the left one or the first line is the main line. So we will find out the impact on the impedance of the first line or the main line, which is also called the driven line, when we are driving the first line, and the other line or the second line, the nearer line, is coming closer or coming nearer to the first line. So the distance between them is short. small distance between them, if they are closely placed, what is the effect on the impedance? Between the lines, if once you have two lines, between the lines there will be mutual inductance and mutual capacitance. That you can see each line will carry a current. If there is a current, there will be an inductance. So each line will have a self-inductance. Now two lines are nearby each other, there are self-inductances, so they will be coupled, the inductances will be coupled, giving rise to a mutual inductance L12. L11 is this self-inductance, L12 is the mutual inductance between the two lines. Similarly, the line will have a capacitance with the ground plane. So ground plane and line both are planes. So two conductors separated by a distance gives you a capacitance. So first line will get C11 dash. For the second line we will have C11 prime, because both lines are of equal dimension that we are considering. Between these two lines there will be some capacitance also, because the two lines have a height, and so there is a plane along the height. There is a plane in first line, there is a plane in the second line. So two metallic planes separated by some distance, that gives you a rise to a capacitance, that is C12 prime. So there will be mutual capacitance. What we have to do is we have to find the effect of these mutual capacitance and inductance of the characteristics impedance of the line. How we are going to do that, and that is important. First, remember the effect of mutual capacitance and inductances. What are the effects of mutual capacitance and inductances? When we bring the lines close to each other, then C12, which is the mutual capacitance, that will increase. Why it will increase? Because of the reduction in distance between the conductors. As you know, C is equal to epsilon A by D. If you reduce D, then D, for smaller D, the capacitance is larger. So this increases due to reduction in distance between the conductors. What happens to C11 or the self-capacitance? The self-capacitance will decrease. Why it will decrease? Because we have two conductors nearby. The second conductor, when we are considering the first conductor, the second conductor or the adjacent conductor is trying to block the electric field coming from the first conductor. The second conductor, on the conductor electric field becomes zero. So the electric field which is coming from the first conductor will become zero on the second conductor. So it will block a portion of the electric field. Since a portion of the electric field from the first conductor will be blocked, so the capacitance due to the first conductor will be reduced. So the self-capacitance will decrease when you bring it closer. Similarly, L12, which is the mutual inductance, that will increase. When they come closer, the mutual inductance will increase. Why it will increase? Because of the current source which creates the field, magnetic field lines becomes larger. When they come closer to the current source, when one line comes closer to the current source, the source which is creating the field, so that will create the magnetic field lines becomes larger. Because of larger magnetic field lines, there will be larger inductance. So L12 will increase, whereas L11 also will marginally increase. This is because of the eddy currents. Hopefully you know what is eddy currents. When they come closer, the currents will be bizarrely affected, but there will be eddy currents. The eddy currents will be caused by the adjacent trace or the adjacent line, will be altering the magnetic line path and increasing the inductance, net inductance. So the mutual capacitance increases, mutual inductance increases, self capacitance decreases, self inductance marginally increases. Now what are the even mode and odd mode in the case of distributed circuits or when we consider the lines? Mode, what is mode in this case? Mode is two special voltage patterns on a differential pair which results in undistorted signal, which means we are sending a signal. This signal is received without any distortion. So if we have sent a sine wave, we will receive a sine wave. If we have sent a square wave, we will receive a square wave. So that is what is called undistorted signal. So, and the voltage pattern on a differential pair, when we have two lines, those are called differential pairs. Mode refers to the voltage pattern that drives the pair. Each pair will be driven by a voltage pattern that is called mode. Now here you see in the bottom I have given you some figures. The left figure is the standard figure. And by the standard figure what I mean is we are sending the mode in the line 1, left line. Right hand line it is 0. No current is there. The current on the left hand line is I1. On the right hand line there is no current. Now this I1 fluctuates between 0 and 1. So that is what, since we are sending a digital signal, it will be between 0 and 1. So that is 1 on the I1, on the I2 it is 0. I2 is equal to 0. This we can also see in terms of odd mode and even. By odd mode, what we have is on the line 1 where I have I1, on the line 2 I have I2, but I1 and I2 are opposite, equal and opposite voltages. So that is odd mode. Equal and opposite voltage or the differential voltage, they drive the pair in the odd mode. In the even mode, you can see I1 and I2 are same. So equal voltage or common voltage, they drive the pair. Now if I add them together, even mode and odd mode, on the line 1, it is always I1 is in one direction, same direction. So it will remain as I1 plus I1 by 2, take the average, it will be I1 plus I1 by 2, that will be I1. On the second line, it is I2 minus I2 plus I2 by 2, that is 0 by 2, which is 0. So that is the standard one. So the standard one, which is the leftmost, can be decomposed into even mode and odd mode. As in case of the circuit, in this case also, we can do it in the same manner. We can do it in the same manner. So the same process, same procedure, everything is followed in this case also. Now, what are the impedances? What is mode we have seen. Now we'll see what is impedances. The special case is impedances. Z odd is the impedance in the odd mode. So impedance of a single trace, single line, either the left line or the right line. Here we will consider the left line to be the signal carrying line. So the impedance of a single trace of the left line when the pair is driven with odd mode is called Z odd. Similarly, the impedance of a single trace when the pair is driven in the even mode is called the Z even. Total impedance is Z even plus Z odd. That gives us the total impedance Z0. So Z odd under coupling, when two lines are there, they are coupled. So Z odd is by definition equal to, as you know, Z odd is characteristics impedance in the odd mode. So Z odd is equal to characteristics impedance is root over of L by C, assuming that there is no loss, because we have assumed there is no distortion, which means there is no loss. So Z odd is equal to root over of L odd by C odd. What is C odd? C odd is the capacitance in the odd mode. L odd is the inductance in the odd mode. Now for C odd, note that C12 is the capacitance of a line when all other conductors are at 0 volt. When driven with an odd mode, the single trace will experience twice as much C21 coupling. Why it will experience twice? Because the charge is double. In the odd mode, the charge is doubled, so C12 is equal to delta Q by delta V is equal to 2 QSC by 2 VSC. So since C12 will be doubled, so therefore the total odd mode capacitance C odd is equal to C11, which is the self capacitance plus twice the mutual capacitance. So C11 plus 2 C12. It is in the odd mode. In the even mode, it will be different. That we'll see later. Coupling, we have seen add the coupling to the pair of lines here. The amount of coupling C12 and say L12, they will depend on the distance between the pairs, and their effect we have already discussed, so I am not going to discuss that anymore. Now what will be L odd? When driven with an odd mode, the current on trace 2 induces a mutual inductive voltage on trace 1. This induced voltage that will create a current that is in the same direction of I1. This in effect lowers the inductances as seen by the signal, since because of this current there will be more flux is being generated with the same incident signal. So this means that a total L odd will be L odd is equal to L11 minus L12. So this is L odd. Z odd will be equal to, using the definition of C odd and L odd, Z odd is equal to root over of L odd by C odd. L odd is equal to L11 minus L12. C odd we have found out, C11 plus 2 times C1. So that will be the Z odd. Similarly, TD odd, on that we will find out root over of L odd into C odd root over, that is like propagation constant. So that is TD odd, that you can find out expression. So Z odd, it will be used when there is coupling between the traces. Z0 and Z odd, these are related to each other. Z0 is the impedance of a single trace when the other line is at 0 volt. Z odd is the impedance of a single trace when the other line is driving it with equal and opposite voltage. Note that when there is no coupling, which means when there is no other line, the other line is at a large distance, then Z0 is equal to Z odd. Now this we have already seen, Z odd expression. Now let us find out C even. C even is required to find out Z even. C even, we have noted this, C12 is the capacitance of the line when all other conductors are 0 voltage. When driven with even mode, the single trace will experience no C12 coupling as there is no charge transfer between the lines, so C12 is equal to 0. If C12 is equal to 0, then C even is equal to C11 only, there will be no contribution due to C12 because C12 is equal to 0. L even is similarly as in the other case. Driven when with even mode, the current on trace 2 induces a mutual inductive voltage on trace 1. This inductive voltage, this creates a current that is in opposite direction of I1. This gives rise to eddy current. So this in effect raises the inductance as seen by a single stress. since there will be less flux that is being generated with same incident signal. So this yields a total A leaving of slightly more value. So A leaving is equal to L11 plus L12. Then Z even using the definition of C even and L even is Z even is equal to root over of L even by C even. L even we have found out L11 plus L12. C even is C11 plus C12. C12 is 0. Therefore, Z even is root over of L11 plus L12 by C11. TD even similarly we will find out TD even is root over of L even into C even. So with that, we come to the end of our discussion on even mode and on mode analysis. We saw two examples. One is a circuit, pure circuit, electrical circuit. Other is the coupled lines, two coupled lines. So we have found out the in the electrical circuit we have found out as an example the admittance matrix. For the coupled lines we have found out the impedances characteristics